Hi guys, I will explain the entire overview on ply steer due to tire tread block from forces on the tire pattern block to displacement and the ply steer. Here I have a quiz for you. What kind of external force on the tire tread block produces the ply steer? Self-aligning moment, horizontal forces produced by flattened tire in the tire contact patch, longitudinal force on the tire contact patch, lateral force on the tire contact patch. We need the unsymmetric beam bending theory to explain the ply steer due to tire tread block. We will form the equation for the deflection of unsymmetric beam bending in terms of moment and stress based upon its physical behavior. To do this, we should be familiar with first the moment of area, second the moment of area, including a Mohr circle and the principal axis, and also concept of neutral plane and neutral axis, and the way to find displacement and its direction. I will explain all the details in the upcoming videos one by one. Each one of tire tread block can be treated as a beam element. Part of tire in the air has a circle shape, but the part of tire in the contact patch has a flat shape. Therefore, circle should shrink to fit the flat shape in the tire contact patch. According to this shape transition, external forces are produced like in the picture. Tire tries to longitudinally compact and to laterally stretch the road surface. You can find the detailed explanation in the YouTube channel EulSeoggy Ko video number E12 here. And also in the reference book, The Automotive Chassis Volume 1 Components Design written by Giancarlo Genta. Therefore, we can model the tire tread block as a beam element shown here. In the tire contact patch, tread block can be analyzed as a beam with both ends fixed. In the edge between tire contact patch and the free region, with one end fixed and the other end partly fixed, except for those with one end fixed and the other end free. In this video, I will not interested in the exact solution for all those cases. Instead of that, I will show the tendencies for developed ply force increments and direction changes depending on the tread block shape. Normally, the cross-section of tire tread blocks are not symmetrical with respect to its vertical and lateral axis to satisfy various performances like wet, ice, traction, braking, noise, even aesthetics. In the beam bending by pure moment M, there is a neutral plane in which no strains and stresses are produced. When you cut the beam in the perpendicular direction to the longitudinal x-axis, you can find the straight line of neutral plane, which is defined as neutral axis. Neutral plane and the neutral axis are not section properties. They are related to both of direction of external load and section shapes. Let's calculate the strain in the beam bending. YZ locates a distance y away from the neutral plane. Length EF is R multiplied by delta theta, which doesn't change during the deformation because EF is the length on the neutral plane, and the length yz is r minus y multiplied by delta theta. Therefore, strain in the x direction can be expressed in this equation. As a result, we can have expressions for strain and stress. The resultant force in the entire cross-section of the beam should be zero because of equilibrium. Therefore, we have these equations. In this equation, we call this integral term a first moment of area. And we have to remember strains are equal to zero on the neutral plane. And the neutral plane and the neutral axis always pass through the centroid of cross-section. Let's consider a strip with this area delta A, which locates a distance y away from the neutral axis. And the beam is loaded by moment m. In this case, moment delta m produces the compression force minus delta F in the strip area delta A. Then substituting the equation 1 for sigma x here, we can get the expression for delta m. Consequently, we can get the resultant moment by the integral all over the cross-section. Integral y squared over the area is called second moment of area, which is very important property in the mechanics of material. Let me explain the sign convention for moment. Sense of moment is plus when that moment produces the compression in the positive half, which is corresponding to the positive y or the positive z. Therefore, moment m is plus in the sagging and the minus in hogging deformation. Here we have the basic equations for calculating second and product moment of area. We have a second moment of area for z-axis and y-axis, and the product moment of area like this. And finally, we have a parallel axis theorem. This will be very useful to get the moment of area distance dz and dy away from the centroid. Another important property is principal axis. Principal axis is defined as a set of axes making product of area equal to zero. Here we have the stress equation in terms of moment and the second and the product moment of area. For the same amount of external load, the size and directions of displacements are different to each other between symmetric and unsymmetric beam. How can we locate the neutral axis? In the neutral axis, the normal stress is equal to zero. Therefore, arranging this equation, we can get the equation of a straight line with slope tangent alpha. This line should pass through the centroid of cross-section. The reason why neutral axis is important is that directions of all the displacements are perpendicular to the neutral axis in the beam bending. Finally, we can reach the equations of displacement, which lead us to get the size and the direction of displacement due to external forces and moments. This figure illustrates the principle that displacement of asymmetric tire pattern block causes ply tear. In this figure, when the force generated by flattening the tire on the road contact surface is applied to the tire block in the negative direction of the y-axis, the displacement occurs from the tire side to the lower right in the direction perpendicular to the neutral axis. Due to the negative z direction component u of this displacement, reaction force is generated in the positive z direction on the road surface. This mechanism produces plysteel. This picture explains the mechanism producing plysteel. All the forces from the tread block make the tire rotate clockwise. If you change the shape of tread block to the shape of mirror symmetry, directions of reaction forces changes opposite. All the forces from the tread block make the tire rotate counterclockwise. You can change or eliminate plysteel using this principle. Therefore, tread block shape is very important to plysteel. The answer to the quiz is horizontal forces produced by flattened tire in the tire contact patch. Here we have a summary. The unsymmetric beam bending theory can explain the plysteel due to tire tread block. Horizontal reaction forces are produced by flattened tire in the contact patch. No strains and stresses are produced in the neutral plane, which enable us to locate neutral axis. Neutral plane and neutral axis are not section properties. They are related to both of direction of external loads and the section shapes. A neutral plane and the neutral axis always pass through the centroid of cross-section. Principal axes are defined as a set of axes making product moment of area equal to 0. A sum of normal stresses is 0 over the section perpendicular to the neutral plane. Directions of all the displacements are perpendicular to the neutral axis in the beam bending. Tread block shape is very important to the plysteel. If you watch the previous videos, you can easily understand the upcoming videos. In the previous video, E37, I explained the various types of stiffness matrix and their elements. Recently, I explained the principle to make in-plane and out-of-plane coupling stiffness elements equal to 0 based upon the sequence order of laminate plies. The next video will be plysteel part 13. I will explain the second and the product moment of area. Please hit the like and catch the brand new videos by free subscription. So, what are you waiting for? See you on next video. Goodbye guys.